Factoring quadratics special cases. So let's recall something called a perfect square. So a perfect square, such as 25, it's a number such that if you took the square root of that number, you would get a 5. And 5 squared is 25. So 25 is a perfect square. 4x squared, similarly, if you took the square root of that, 4x squared, you would do the square root of 4, which is 2, and the square root of x squared, which is 2, which is x. So 4x squared is a perfect square because it can be made by multiplying a number by itself, or a number and a variable by itself. And similarly, x plus 3 squared, if I took the square root of that, I would also just get x plus 3. So there is a little thing here with perfect squares that will help us factor specific trinomials. So if you recall, in general, if you had a factored a plus b and it's being squared, if you expanded it using the distributive property, you would get a squared plus 2ab plus b squared. So just to show you that one more time, so a plus b squared can be written as a plus b times a plus b. And if I expanded this, I would get a times a, which is a squared, a times b, which is ab, and then b times a, which is another ab, and then b times b, which is b squared. And if I collect the two terms in the middle, I would have a squared plus 2ab plus b squared. Now, when I had b times a and I wrote ab here, that's still allowed because multiplication is commutative, so I could write the order instead of b times a. It's the same thing as saying a times b. By writing it as a times b, I can show you that a and b, when I add them together, makes it much more clear that it is 2ab. Okay, and so here is the expanded form of that. And if you want to go in reverse, you can go in reverse. When you factor it, you will get a plus b squared again. Okay, so when factoring trinomials, if you notice a pattern in the coefficients, it will help you factor them. So you have to ask yourself, is this first term a perfect square? Is the last term a perfect square? And is the middle term 2 times the first term and the last term, which is what we have here, 2 times the first term and the last term? And if these three conditions are met, then you can employ perfect square factoring, which is just writing the first term, the square root of the last term, or the square root of the first term and the square root of the last term in brackets, and then square it. Okay, so in general, we use this formula to help us factor perfect square trinomials. And the difference between the first and the second one is just the change in signs from plus to minus. So let's look at some examples here. X squared plus 6x plus 9. So you ask yourself, because the first term is squared term, is x squared a perfect square? It certainly is. The square root of x squared is x. Is 9 a perfect square, which is the last term? Well, that's yes, so because the square root of 9 is 3. And so is the middle term 2 times the first term times 2 times the square root of the first term times the square root of the second term, just as we had set up here. Okay, and it turns out to be, well, let's see, square root of x squared we know is x, square root of 9 is 3, so 2 times 3 times x is 6x, which means it is yes. So therefore, if I wanted to factor this, all I'd have to do is write the brackets and square root of the first term, which is x, square root of the last term, which is 3, and then write your squared outside, and because it's plus plus, we're going to write a plus, so x plus 3. Okay, so what about some others? X squared plus 9x, so 9x squared plus 24x plus 16. So let's check. 9x squared is, square root of 9x squared is, so the square root of 9 is 3, square root of x squared is x. The last term is 16, so the square root of 16 is equal to 4. So far so good. So let's check 2 times 3x times, 2 times 3x times 4, which is equal to 2 times 3 times 4, which is 6 times 4, which is 24, and then we have x, and that's exactly what we have here in the middle term. So the middle term is 2 times the square root of the first term times the square root of the last term. And if so these three conditions are met, we can say that 9x squared plus 24x plus 16 is equal to, in factored form, would be your square root of the first term, which is 3x, square root of the last term, which is 4. All terms are being added, so you're going to put plus in the middle, and then your brackets, then your squared sign. So 3x plus 4 squared. Okay, let's try this one. X squared minus 4x plus 4. Well, if I took the square root of x squared, we have a perfect square, so that's x. The last term, the square root of 4, which is 2, so 4 is a perfect square. And if I took 2 times the first term, which is x, times the last term, which is 2, so I get 2 times x times 2, which is 4x. Okay, and the minus sign is still fine, so we had minus 2, and also minus 4x. So exactly what we have in the middle. So the factored form would be so x squared of minus 4x plus 4. The factored form of this would be brackets, square root of the first term, square root of the last term. There's a minus sign this time because we're starting off with a minus in front of our second term here. And so it's x minus 2 in brackets squared. And you should always check just to make sure your factored form is correct by expanding it once more. So that's factoring perfect squares. Let's look at another special case of factoring, and let's call this one difference of squares. So remember, the difference of squares is exactly that. You're subtracting one square from another. So let's say x squared minus 4 is equivalent to x squared minus 2 squared. You just rewrite the 4 as 2 squared. And so you see a difference of squared terms. So what happens? What does that look like when you're expanding and factoring them? Well, if I took a plus b in brackets times a minus b in brackets, and I expanded this, the distributive property tells us, well, I would have a times a, which is a squared, a times minus b, which is a minus ab, b times a, so plus ab. Again, commutative property allows me to switch them because they're being multiplied. And then b times b, which is so minus sign, so minus b squared. And then you see, notice the two middle terms, they cancel each other out because one is minus and the other one is plus. And then you're left with a squared minus b squared. And this is your difference of squares. And so going in reverse, you can take a difference of squares and then write them as your two brackets and the square root of the first term and this last term in each bracket. And one bracket will be adding and the other one will be subtracting. So when factoring binomials, if you notice the pattern, in the coefficients, it will help you factor them. So ask yourself, is the first term a perfect square? Is the last term a perfect square? And is there a minus sign between the two terms? So, and if so, you'll have a factored form that looks like this. Square root of the first term plus the square root of the last term in brackets. Same thing for the other bracket. The only difference is that your signs are positive in the first bracket and minus in the second bracket. So in general, you can use this formula. A squared minus b squared is equal to a plus b in brackets times a minus b in brackets. All right, so let's look at a couple of examples here. So p squared minus 225. So check, is p squared a perfect squared? Well, yes it is, because the square root of p squared is equal to p. 225, well, you check on your calculator if you need to, but it turns out the square root of 225 is equal to 15. And is there a minus sign? Yes, there is. So then all you'd have to do is write the square root of p squared, which is p, and then the square root of 225, which is 15. Do this again for another bracket, so p and 15. Make one bracket plus and the other one minus. And there's your factored form. 49m squared minus 100. So you check. Square root of 49m squared is equal to square root of 49 is 7. Square root of m squared is m. So that is a perfect square. square root of 100. So again, as you're doing the difference of squares, ignore the minus sign. So when you're doing if you're checking to see if it's a perfect square, the square root of 100 is 10, so that is a perfect square. And so you see 49m squared minus 100. The third condition is you have to have the minus sign in the middle. And so if you do, you can write out the factored form as brackets. The first bracket, your square root, your perfect square, so 7m. The square root of 100 is 10. Square root of first term is 7m, and the square root of the last term is 10. Last term is 10. So then 7m, 10, 7m, and 10 in brackets make one bracket plus and then one minus, and there's your factored form. The last one. Now again, as you're factoring everything, you always have to check to make sure the first term is a common factor. Because if it is, it makes life a lot easier. So it turns out I can divide 6 into 150 25 times, right? So factor out a 6 first, so x squared. 150 divided by 6 is 25, so minus 25. And then that's what we're going to say first is we're going to common factor. Okay, and then x squared minus 25, that's my difference of squares. If you notice, I have the square root of x squared is equal to x, and the square root of 25, which is equal to 5. And there's a minus sign in between. So I can write x squared minus 25 as 2 brackets, x, and the square root of 25 is 5, so 5 goes there, x, and 5 goes there, make 1 plus, make the other minus, and don't forget you still have a 6 in the front, so you make sure you put a 6 in your answer as well. Okay, so as with all factoring methods, check to see if you have a common factor first, if a is the common factor, right? Common factor first, and then check to see if you have a difference of squares in your remainder of your other factor. Okay, and that ends this lesson.